presenting for math project 2, that is free oscillation group 7. Okay, what is free oscillation? Free oscillation is the motion of a system that vibrates after being disrupted from its equilibrium position and then allowed to move without any continuous external force acting on it. Okay, for quick understanding, imagine you have a spring with a toy hanging on it. If you pull on the toy down and let it go, the toy will move up and will go down. Nobody is pushing it or pulling it anymore, but it's still moving because of the spring trying to bring it back to normal position. This is called free oscillation.
Okay, for this slide, we will be looking at the formulation of the second order differential equation that describes the oscillation. The oscillation happens when a mass spring system is discharged from its equilibrium position and then released without any external force acting on it. The general equation given this is m d power 2 x per d power 2 plus d dx per dx plus kx equal ft, and this single equation is the foundation for everything we analyze in this topic. Okay, for this is the breakdown for each term that is in the formula. M for mass or inertial effect, P for damping coefficient, friction or resistance effect, K for spring constant or restoring force, and X for displacement from equilibrium position.
Now we are going to see the solution for the questions. So for example 3.11, if a mass spring system with an iron ball of weight 98, net tonnage can be regarded as undamped at free vibration and the spring is such that the ball stretches it 1.09 meter. How many cycles per minute will the system execute? What will be its motion if we pull the ball down from rest by 0.16 meter and let it start with zero initial velocity? So first of all, we know the weight is 98 Newton, so we have to find the mass. So 98 times mass times 9.81 will get the mass as 10 kilograms. So to find the spring constant, W over delta E. So delta 98 over 1.09 will get as 89.91 Newton meter. So to find the angular frequency, W equals to square root of K over M. So once we allocate the spring constant 89.91 and the M is 10, we'll get as 2.998, and then if we convert it to radian per second, we'll get as square root of 815 per 5 radian per second. Next, we gotta find the circle per minute. So just now we already get the angular frequency as 2.998, and then when we divide it by 2 pi, we'll get as 0.4772 cycles per second. So when we times it with 60, we'll get at 28.63 circles per minute. But we gotta recheck our answer. So for recheck, we have to use the formula. So m times x double prime plus k times x equals to 0. So 10, we know the m is 10. 10 times x double prime plus 89.1 x equals to 0. So x prime equals to 8.91 x equals to 0. So m square equals to 8.991 plus 0. So m equals to plus minus square root of 815 per 5 times I. So we'll get x equals, when x equals to 0, we'll get as 0.16. When x equals to x prime equals to 0, we'll get as 0. So using x equals to 0 equals to 0.16, we know that the a is 0.16. So when we put it inside the formula and differentiate, we'll get as x prime in bracket t equals to negative square root of 815 per 5 a times sine in bracket square root of 815 per 5 times with t close bracket, and then plus square root of 815 over 5 plus b cos in bracket 815 per 5 times with t. So using x prime equals to 0, we know that the whole equation is equals to 0, that B equals to 0. So motion of the ball equals to x in bracket t 0.16 cos in bracket 815 square root of 815 over 5 over t. Then we know that the motion of the ball is equals to 28.63 cycles per minute. So next, where can be this applied? So in daily life, we can apply free oscillation, or more as known as second order derivative, can be used at vehicle suspension systems, building vibration analysis, shock absorbers, machinery, vibration control, and mechanical oscillators. And that's all from us. Thank you.
He and Abu are driving to the university.
It's a nice day for a drive.
Yes, but watch out, there's a speed bump ahead.
Whoa, did you feel that?
Yes, the curve bounced up and down a few times.
I always wonder why that happened.
So let's ask an engineer.
Excuse me, can you explain why car bounced after hitting the speed bump?
Of course, it happens because of the car's suspension system.
What's a suspension system?
It's a combination of springs and a shock absorber that helps make the ride smoother. When the car goes over a bumper, the spring compresses and stores energy.
Then what happened?
The spring pushes back and makes the car move up and down.
So that's why the car is bounced.
Exactly. Engineers use a second order differential equation to model this motion.
What does this symbol mean?
It's a car's engineer to predict how the car moves.
That's right.
Explain it in why doesn't the car bounce forever?
Good question. That's because of the shock absorber.
What does it do?
It reduces the bouncing and helps the car return to normal quickly.
Bounce, and stop.
Now I understand.
Without a suspension system, driving would be very uncomfortable and unsafe.
So springs exert the bulk and shock absorbers reduce the bouncing.
And engineers use second order differential equation to design better suspension system.
Exactly.
Thank you.